Hello everyone, can you hear me? Great.
Hi, welcome back, everyone. Very sorry for that little confusion there. Hi, Tibor. Good morning from Slovakia. That's nice to hear. All right, so let's start off. Hello to everyone. Welcome to our introductory webinar on big data and Hadoop. My name is Anjana, and I'm part of the team here at No Big Data. I'll be taking you through what to expect of this session. Please make use of this time to let us know about yourselves as well. So the first half of the session will focus on understanding big data and why it is relevant in today's world, followed by a 10-minute break, and then we will move on to Hadoop architecture. For those who are taking notes, you can please sit back and relax. We will share this presentation and recording with everyone here. No Big Data stands out for having instructors who encourage questioning. So please keep those questions coming. Since this is an introductory session, we have a lot of attendees, which is why everyone is muted. Our instructor for the day will read out a question before answering it. You can help the instructor by keeping your questions short and easy to understand. So the chat window is your primary mode of communication with the instructor today. This session is one of our 11-part course for Big Data and Hadoop, but on its own will suffice as an introduction to big data technologies. For those who will be joining us for the rest of the course from the next session will have fewer attendees and it will be on a different, more interactive tool. So before we move on to the session to Big Data and Hadoop, let me just introduce you to Know Big Data. We have instructors who are industry experts. You will soon find out for yourself how true that is during the session. As part of the course, we provide access to Cloud Labs, which is a cluster that you can use to play around with whatever you learn during your classes. This feature is unique to Know Big Data and gives you a real world feel. So course takers are also given lifetime access to our learning management system, which will include all the presentations, recordings, assignments, and project work. At the end of the course, you will get a real-life project to complete, and you will receive a social media compatible certificate at the end of the project. You will have 24/7 online support. You will also be part of our alumni group, which will keep you posted of new job opportunities and help you stay updated and connected.
All right, everyone. So that was Anjana's introduction, and I'm Sandeep Giri. I'll be the instructor for today. And so, it's a 11-part course, and today we will be discussing about big data and Hadoop architecture. All right. And so regarding myself, all right. So Before I introduce myself, let me just go through your introduction. So we have a great audience today. We have Samir Shah, and Samir Shah is a senior data implementer and is looking for insights into big data. And then we have Kiran. Kiran is a senior Java developer. Great, great to know you, Kiran. And then we have Matthew. All right, we have Karupaswamy from Chennai. Okay. We have Satyendra who has 9 years experience, 9+ years of experience, and is new to big data world. So everybody is probably new to big data world. Satyendra, welcome to the class. All right, all right. We have Nijesh from Bangalore, and we have Tibor from Slovakia. Great. And we have Lenny Kotiar and a, a BI practice lead at Coherent Solutions located in Minneapolis. Great, great. Anindita's question is, will you help in updating the resume? Yeah, so we'll just review your resume and we'll give you the suggestions. So we have Vaibhav, all right, and Vaibhav Srivastav. We have Kunal, okay, all right. Kunal is at SAP Labs, Bangalore. Okay. We have Deepak. Deepak is working with TCS, having almost 3 years of experience and currently working in mainframes. All right. We have Parmeshwar Nayak, who is a QA engineer. All right. We have Matthew, who is working as a web developer in Atlanta. Great. Great. Okay. So Nijesh has been working with Python and Java programmer primarily, and working with machine learning, but new to big data. Great, great. We have great set of candidate. Should we? I think we should start now. So we have John Sakirias. He's from New Jersey, working with ENY. Brilliant. So we have a great set of audience from all geographies and from various technical background. So about myself, I'm Sandeep Giri. I passed from IIT Roorkee in 2002, and then I worked with a company called DE Shaw, where we were having a largest cluster at that point of time. We had a 10,000 node of cluster in 2002. So we were working on big data before probably most of the companies. And afterwards, I started a company called Tbits Global for document management system. Afterwards, I joined a company called InMobi, where I built recommenders and similar big data solutions in my a small sojourn there. Then I joined Amazon. At Amazon, I built a system like Storm, Apache Storm, and along with my team, and which is being used in other projects as well at Amazon. And along with that, we did a very large image churning of Amazon detail page. The Amazon detail page, which you see in uh, the page which has the buy now button. So there is a big image on the laptop. So that need to be selected amongst a lot of images. So I worked on that one, and yeah. So that was about me. And then in last year, we started No Big Data because we found that there's a big gap between the instructors and the students. As in, there's a big technical gap in instructors. Most of the instructors were people who have been traditionally the instructors, not the developers. So that is one thing which we are trying to change. All right. So that was my introduction, and if you see that most of my career I have been working with big data mostly, and all right, all right. So in today's class, we will be talking about big data, and so let's start with asking you the question: what exactly is big data? What do you understand by big data? Yeah. All right. Kunal says large volumes of structured data and unstructured data. Okay. Okay. Anybody else? Matthew says big data is a high volume data coming in at high rate. Tibor says number of terabytes and more. Parmeshwar says high huge data which cannot be handled through RDBMS. Okay. Webber says large amount of data requiring distributed architecture to process. Brilliant. Nijay says that the use case where the volume and veracity of data is too high and is a mix of structured and unstructured. All right. Neha says that huge amount of data out of which you can't make anything unless you structured it using software. Okay. All right. All right. Great. Great set of answers. So So the definition of big data is quite vague, and so we'll try to concretize and we'll stick to that definition across the whole course. Okay, so big data is simply the data of very big size, okay, which you cannot process using the usual tools. Now, the most important aspect, as Webb have also said, that it's a distributed architecture. Okay. So whenever you have a problem which you cannot solve using a single computer, no matter if you replace your single computer with a supercomputer, even if you are not able to solve, then you would require a distributed architecture, which means multiple computers trying to solve a single problem. Okay, the data could be structured or unstructured. All right. Now, Now, what exactly do we understand by distributed architecture? A distributed architecture means that multiple computers connected together to solve a particular problem, right? While parallel computing means so generally distributed architecture is confused with parallel computing. Parallel computing means there is a memory, single memory, and there are multiple processors who are trying to coordinate with each other using this memory. So for having a great parallel computing environment, you need specialized built computers, while for distributed computing you don't require specialized built computers. You can connect your usual computers to network and then start getting your work done. The only special thing you require in case of distributed architecture is the software. The software should be capable enough to handle to distribute the work across the cluster. Okay, so that was so our primary focus will be all the components that we start with, starting with HDFS, then MapReduce, then we'll talk about Pig, Hive, Pig, Hive, HBase, and then Flume, Scoop, Mahout, Zookeeper, and Spark. All of these components have a single commonality between them, which is all of these softwares run on multiple computers. And we will be discussing these softwares, these tools, these techniques in this course. Okay, so the most important thing to remember here is the distributed architecture. All right, and we will understand why it is the distributed architecture that solves the problem, not the single computer systems. We will talk about it. All right, so I hope the difference between the distributed computing and parallel computing is clear to all. So in parallel computing you have these specialized build computers which has multiprocessors, and all these processors run on the same machine and coordinate with each other over memory. Okay, while in case of distributed computing you have these normal computers which are connected. You don't build the specialized hardware, and you run them over the network, and run the special software which can coordinate with each other. Okay, all right, there was another statement, the fourth one, which says structured or unstructured data. Your data, basically big data is a data of high volume which you cannot process with usual tools. It could be structured or unstructured, for which you would require distributed computing. So what does it mean by structured or unstructured? All right, so structured means when we say talk about data kinds, it could be structured, unstructured, and semi-structured. So data which is structured is the one which has fields, okay, but does not have sorry, structured. In case of structured data, we know what are the fields in the input, as well as we know the data types of each of the input. Okay, for example, a relational database. In a relational database, we know very clearly that what exactly, what are the fields in our input, as in these are the columns in our input, and what are the data types of each of the columns. Okay, therefore a data in a relational database, the table or a collection of table, is considered as structured data, while a a semi-structured data is a data where you know what are the fields in the input, but you do not know the data types. For example, in case of a CSV file, comma separated values, it's a format where the various values are stored by comma separated and various records are stored in new line separated. So in such case, in case of comma separated values, we do not have any clue about the data type of each of the columns. The CSV format does not provide you an arrangement to pass on the data type of each field. And therefore, when you are given a CSV file, you would know that what are the fields in the input data, but you would not know their data types. Therefore, you will either have to infer the data types, or I mean guess the data types, or you will have to use some external information. Okay, so that kind of data is called semi-structured data. Now, on the other end, we have unstructured data. In case of unstructured data, we do not know the various fields. We do not know the various fields in the input. Neither we know the fields nor we know their data types. All right. So take a case of, say, Apache logs. What is Apache logs? When you have a website running and when users are accessing it, the server keeps on creating the logs. So if you look at these logs, these are plain text files. Okay, and you don't really have. I mean, if it's a new system, if it's a new system, you may not know what exactly, how exactly are fields arranged in this file. Okay, are they fixed, are they kind of in the fixed format, or they are comma separated, or how, or tab separated, or how, what exactly is the format of the plain text file? Or take a case of video or other formats where you do not have a clue about the structure of the input file. Okay, for that, to infer the structure, there is no clarity. So for inferring the structure, you might have to parse, as in you have to do a little bit processing to 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 infer the structure, to understand the structure. Okay, so it's not readily available. All right, Nijis is saying, could you please share your screen? Suddenly the screen sharing is off. Is everybody able to see what on my screen? Yeah, everybody can see, Nijesh. I think there's something wrong with your machine. All right, all right. Okay. Now, this is the traditional definition of big data, which was propagated by IBM. This just tells you the various characteristics of big data. So, for example, the first characteristic is volume, meaning the data at rest, the data you have gathered or you have gathered today or yesterday or before that. Okay, so the first characteristic of big data is volume, meaning it might be the volume because of which you require distributed computing. Okay, or it could be the velocity as in number of requests coming from the user, or if number of requests are coming from the users are high, then we call that it's a velocity, it's a problem of the velocity. Then the variety as in data in many forms. Okay, so and variety stands for two things. First, the kind of data you are processing. Second, the kind of problem you are trying to solve. Okay, I will tell you a couple of examples in case of variety. So volume and velocity is obvious that, for example, if you have so much of data, you cannot store it in a single hard disk. You require multiple hard disks, and hence you would require multiple computers to store it, right? And that's why the volume characteristic of the data would force you to have a distributed computing. Similarly, if the velocity, as in number of requests that are coming from users, are very high, to cater all of them in time, you would require multiple computers to handle these requests. And for example, in case of Facebook, every moment everybody keeps on refreshing their screens, and there are millions of requests that are going to Facebook every seconds from all kinds of devices. And therefore, the velocity which Facebook is receiving are really, really high. Therefore, all right. So velocity also can push you to move to a distributed architecture solution, meaning multiple computer systems. Now, the third one is variety, as in when we have We might have the kind of problem we are trying to solve, we might have the kind of problem of very different kinds. For example, let's say you have a huge map of a country, and although this map might be of say 100 gigabytes of size, so the volume is not too much of a problem, neither is the velocity. Okay, but because data is not moving very fast, you are given a stationary map of a country. Now what you need to do is, in a reasonable amount of time, you have to find a path from one place to another in this map. Okay, so if you have to find a path from one place to another in this map, what will happen is that your normal processing requirement, normal computing will not suffice. Finding a path from one place to another is a complex process. Even if you have a supercomputer, finding a path on a map is very difficult in a reasonable amount of time. Okay, therefore for these kind of processing uh, you might require a distributed computing. Okay, meaning you might require multiple computers to solve the problem at hand. Now the last one, which is veracity, uh, to me it is more of a addition at a later point of time, and they keep on adding every once in a while new v's. Okay, now the veracity part, when we talk about veracity, it is basically data accumulated due to confusion or due to unclearness, uncertainty. For example, let's say your role is to find out you want to do some analytics on temperature data across the globe. Okay, say you are doing some prediction based on the temperature data of the whole world. Now you found out that there are 10 different kind of data sets. Say first data set contains the temperature data every minute. Second data set contains the temperature data every second. And third one contains every minute but gives you the data per GPS location. Third one has more of the finer granularity, I mean fourth one. So imagine there are these 10 different kind of data sets. Okay, now which one to keep and which one to ignore, or which one to discard, till the point you reach to this conclusion that okay, this is my data set, this is my temperature data. Out of these 10 data sets, you will have to store all these 10 data sets, and then you have to process and compare these 10 data sets. And that is one of the big reasons why we end up having lot of big data. So in a way, veracity might cause a lot of volume, and therefore the veracity characteristics causes you for distributed computing, forces you to move to distributed computing. All right, make sense to you? Any questions on this? Okay, so I mean, feel free to ask questions. These sessions, in these sessions are meant for question answers. Okay, because video recording you can find elsewhere. There are so many sources, but these sessions are mainly for having a lot of questions. Nijesh's question is, but doesn't veracity sometimes an input for predictive analytics? Yes. So yes, Nijesh. Probably every data is an input for predictive analytics. Okay, every characteristic, be it volume, be it variety, be it veracity. Yeah. All right. Any other questions? Okay, just to check if you are with me or not. So, how many bytes are there in petabytes? All right. Before we move on, we have an important question. S- Okay. So, Kiran is saying, can you give any other example for veracity? Okay. So, I mean, if you look at your organization, there'll be so many. Let's pick up any organization. You will see so many tables, and you will find that some data is inconsistent, some data is okay, but which one to pick, or whether there is a certain data set is a derivative of another one. Okay, so because of those confusions, you might end up storing a lot of data, meaning veracity leads to volume and hence the distributed computing. So Neha's point is, will veracity not lead to errors in prediction? So it might or it might not. Neha, it will all depends on your understanding of the data based on various data sets. What kind of algorithm will you use to pick up the right data? Uh, Okay, that I hope, Kiran, that I was able to answer. All right, great, great. So, uh, Anandita, you're saying 10 to the 5? Okay, all right, great, great. Yes, yes, that's correct, Anandita. It's 1000 to the power 5. That's correct. All right. So, yes, so it's 10 to the power 15. Okay, and almost everybody is correct in this. Great, great. We have one more question from Nijesh. If veracity is bottleneck, algorithm to solve have higher chance of being quadratic time. Okay. Mm, okay. Mm, I'm not sure if that statement is correct, but yeah, we can have an offline discussion about it. All right. Okay. So we have a very good question from Weber. Does veracity means even when you know that the data being used for predictive analytics is incomplete, but you still go ahead with the analysis and thereby account for the uncertainty by use of big data. Okay, so yeah, so his point is that does veracity means that even though we know the data is uncertain, still we utilize this data to do our predictive analytics or some other conclusion or some other insights into the data. In a way, yes. even though we feel that a small portion of data has got deviations, okay, still we believe that if the data is big enough, those small errors will be corrected over because of the big data. Okay, because of the big data, those will be corrected. Okay, because if you have a large data, then the smaller deviations in the data can be ignored. So that is another way of looking at it. But veracity generally means that the data is inconsistent, incomplete, and we do not know which data to pick. Therefore, we need to process this data, analyze this data, and pick up the right one, which is of the use for us. Okay, all right. Yeah. Vijay says, I guess in this scenario, data will not be uncertain. It may be incomplete. Okay. Predictive is not 100% correct all the time, anytime. Yeah, that's correct, Kunal. And all right. Neha says, can't big data be solved using SAS and R? Okay, that's a good question, Neha. And as we talked earlier, that most of these problems say, for example, SAS or R, they work on a single computer. As the data starts growing bigger, they are pretty useless. After, say, the data goes beyond your RAM size, it won't be of any use. Okay, the R or SAS cannot be used after the data grows to maybe some, let's say you have 4 GB RAM. If data grows to 4 GB, your R or SAS cannot be used. All right, and that's the reason why. Okay, so it's not the algorithm, it's many things, including the computer's resources for which we require distributed computing. Okay, a way to remember the petabyte thing, you can have this table as in kilo, mega, giga, tera, peta, and each one is a multiple of 1024 of the previous value. Okay, so Vijay says the fundamental difference is R or SAS for useful for analysis, but not for processing. Okay, so analysis is a form of processing, Vijay. The fundamental difference with respect to the processing is is basically the distributed thing. Okay, Nijesh's question is, distributed nodes were existent when Google came in late 90s. What is special in big data nodes? Okay, very good question. So it's a very good question. So let me take these two more questions and then we'll move. Okay, so yes, so distributed computing existed, but that distributed computing was limited to only few players in the industry. If somebody else tries to build distributed computing system by themselves, it was a Herculean task. It was a very difficult task, and most of us did not, I mean, could not build such systems. Okay, it was because of Google themselves, as you said, that it was because of Google. Google published a couple of papers, and then Amazon also published a couple of papers, because of which open source world built the solutions which could be utilized by rest of the world to solve their big data problems. Okay, So that was the new thing in case of big data, that it became possible for everyone to start churning big data. Okay, because these tools are freely and openly available to everybody now. Okay, now Neha's question is, okay, yeah, all right. Your question was valid, Neha. And the main reason was, as again, I will enforce that with SAS and R, after a point of time, CPU or the RAM becomes the limitation. We will talk about this as we go forward. All right, there's one more question, and then yeah, we will discuss further. So Kunal's question is: most of the companies load into in-memory DB from Hadoop system. With Spark, do we need to do ETL? Okay, so see, the definition of ETL tool has also changed. Earlier, earlier we thought that even the ETL kind of problems are very easy to do. When we say ETL means there is a huge data, and then you have to extract the information from it, then transform it, then load it. Extract, transform, load. And we form a meaningful structured data out of our unstructured data. That is the objective of ETL generally, or transforming one structured data into another. So again, ETL, while it was earlier a different kind of, totally a different set of tools, but ETL itself is not possible on big data using the traditional tools. Okay. Reason being, when we talk about data, it's not only the processing, it's not only the RAM or CPU, it's also the rate at which you can read the data from the disk. And in most of the cases, it is the disk at which from which we are reading the data becomes the bottleneck. You will see that as we go forward. So Ganeshan's question is how to integrate big data framework with the web application. Just name of the framework is enough. Okay, so the question need to be answered in a little better manner. I have also answered it on our forum, and I'll try to answer this way. Maybe after we cover first half, then I think I should answer this again. All right. Okay. All right. So I'll try to answer your question after first half. Okay. Then it will make more sense. Thank you, Neha, and yeah, for your tip on remembering the petabyte. All right. So now main question to which I want to ask all of you, as we talked earlier, that big data is all about processing over data which need to be processed over distributed computing or distributed architecture. And petabyte is about 10 to the power 15 bytes, right? So my question to all of you is petabyte a big data? Now, before you ask me that, it all depends. Tell you this. So what I want to do is every day in the evening, I want to churn 1 petabyte data to count how many vowels are there in my data. In my 1 petabyte data, I want to count every day how many vowels are there. So question to you is this kind of processing considered as big data processing? Okay. So we know how much is petabyte, we know what is big data. So do you think this kind of churning of 1 petabyte, the very basic one, just go through the data once every day, is that kind of processing big data processing? All right. Susil says that no, I don't think as petabyte can be handled in my local system of 8 gigabyte with i7. Interesting, interesting. So yes, we will try to understand that part. Is that really possible or not? Okay, is that really possible or not? So Kunal says depends on how fast you need the answer. Okay, okay. Let me repeat. So all I want to do is go through the data once every day, which means the TAT I'm expecting, the turnaround time I'm expecting is at most 24 hours, nothing beyond 24 hours. Now Matthew says that it would take too long to process 1 petabyte data on standard computing if you could do it at all. That's correct, Matthew. Okay. Kunal says that, yeah, it all depends on how fast you need the answer. Second is, and what kind of system are you using? So let's imagine that the system which we just talked about, say 8 GB RAM or maybe whatever specifications you want to pick up, you can pick up. Okay. Whatever specific, you are free to pick up any specification you want. Kunal. Kiran says we cannot load 1 petabyte file into local memory. Okay, but do you need to load it in a local memory? Leonid says that it all depends on whether the traditional technologies can handle the computation. Yes, that exactly is the question. If not, it's a big data. Yeah, so instead of saying traditional technologies, we will say that instead of using a single computer, do we need to, are we being forced to use distributed computing? Neha says, no, I don't think so. You need supercomputer to process it. Humans can't do it manually. Okay, so I'm talking about a single computer or the distributed computer. So do we require, can we handle it even with a really, really good supercomputer? Okay. Kiran says that it should be split it into small size to be loaded. That's correct, Kiran. Yes. Correct, correct. I've got a good answer. So above says since the reading of the data itself will take time, you have to read through entire data daily. It's a volume problem. That's exactly is the problem. Okay, so yes, reading 1 petabyte data takes a humongous amount of time. I will show you why. Because the hard disks are slow. We will go into numbers quickly. Okay. Kunal says, yes, it's a big data problem for me. Satyan says, we will be limited by disk read speed on a single computer. Doesn't matter how fast the processor or RAM is. Great. Thank you, Satyendra. Yes, that's exactly is the problem. Great. Thank you, Nijesh. Yeah, now you got it right. So, yes, 1 petabyte data is a big data. Most of the existing systems cannot handle it. We will talk about it. Why? Now, my next question is how much time does it take to read 1 terabyte data? Anyone? Just anyone? How much time does it take to read 1 terabyte data? Can anybody answer? Several hours. That's correct. Now you can think of the petabyte, right? So, so 1 GB takes around 5 seconds to read, and therefore 1 TB would take around maybe 5 6 hours. All right. So approximately it takes 6 hours. Okay. Although some hard disks would be better, they might take maybe 4 hours, might be 5 hours. There might be slower hard disks which might take more than 6 hours. Yeah. But it will be in hours. No matter what kind of hard disk are you using, it will take hours to actually load 1 terabyte data. Meaning, if you have 1 terabyte movies and you want to copy it to another disk, then it will take minimum of 6 hours. If you have really good computer, everything is great. Still, just copying the movies from one disk to another will take around 6 hours. Now, when you read this data, neither your RAM or processor, no matter which Pentium you have, which supercomputer you have, it will still takes 6 hours. All right. Now this is something which we all need to understand. All right. So therefore, if 1 terabyte takes 6 hours, so 1 petabyte is going to take 6,000 hours. All right. If one terabyte takes 6 hours, 1 petabyte would take 6,000 hours, and therefore a single computer in no way neither can store 1 petabyte data nor it can process it. Therefore, 1 petabyte data is big data. All right. Now, now this is a traditional chart, which is basically a evidence that the data has started growing exponentially after year 2002. I mean, it's a beginning of digital age. The digital storage has started expanding. I mean, the data which is being stored in digital storage have increased tremendously, and the analog has been shrinking. Analog is like books and tape drives and that kind of recordings. So that is anyway shrinking, while the digital storage has been increasing every day. Okay, and why did it is it happening that way? Okay, so the answer is twofold. First, the smartphones, and second is connectivity, meaning devices and connectivity. So on one hand, after 2000s, the devices have become the cheaper, faster, and smaller. These are the three criterias of any hardware manufacturer: cheaper, faster, and smaller. And that has resulted in a 1 billion device called mobile, which basically has the ability of a supercomputers of 80s, a supercomputer of actually 90s. It was equivalent to the mobile phone which you have right now. So on one hand, the devices became so popular and easily available and cheaper, faster, and smaller, because of which a lot of data could be generated. Okay, you can take pictures, you can do lot of things. And on the other hand, the connectivity improved a lot. Okay, you have 3G, 4G, and you have Wi-Fi, you have all kind of connectivities to 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 transmit the information. And whenever you transmit the information, the data duplicates. Okay, therefore, for example, I'm giving this session, and right now the around at by the end of this session I will have transmitted around 2 gigabytes of data. While if there are 50 members in this class, the total data transmission that would happen would be around 100 GB. Therefore, the connectivity basically most of the time replicates a lot of information, and therefore combination of the two, the phone and the connectivity, has led to this increasingly overwhelming the rate at which the data is being generated. Okay, and both of this, the device and the connectivity is being utilized by these nice applications such as YouTube, Facebook, Twitter, to give people really useful utilities. All right. So yeah. All right. So now my question to all of you is, based on what we have just discussed, which components impact the speed of computing? Is it CPU, memory read speed, disk size, network speed, or all of above? So I'm Kunal. I'm talking about in general, not only our problem at hand. I'm talking in general. Which components impact the speed of computing in general? Correct. Great. So now everybody has understood it's all of them. Whenever we talk about computing, we do not talk only about CPU or RAM or RAM speed. We always the overall computing speed is a function of all of these components. Okay, great, great. All right. Again, let me reinforce whatever we have just talked. To process the data in a computer, we require a CPU, a RAM, a network, and a disk. Okay, and whenever we are building a solution, we basically we keep on sifting whenever we are handling the data and we are not able to do it on time. Whenever we optimize, we basically sift the load from one component to another. For example, if our RAM is insufficient, we will try to put it in the disk. Okay, and then it'll start getting slower because disks are slower. Okay, similarly, if disk is not sufficient, we move the data to the network, and then network becomes the bottleneck every time we try to read the data. And at other end, if the RAM is full and we have to process, our problem is complex, then we might have to process the same data multiple times, and we have to, I mean, we it might take more and more time for CPU. But generally it's not the CPU, it's either the RAM or the disk speed which are the bottleneck in the game. So, I mean, this is an interesting observation. You will, if you ask any sysadmin, they will tell you that it is generally the RAM which is the bottleneck, or it is the disk read speed which is the bottleneck. Okay, although all these four components would become the bottleneck, at least one of them becomes such a big bottleneck that you o- cannot overcome, and that's when you say that we require big data. So whenever we to handle the big data, at least one of these four components will become such a big bottleneck that you cannot overcome by upgrading your RAM, CPU, or network. Okay, you cannot solve those kind of problem by upgrading any of this. Instead, you might have to move to distributed computing, meaning you have to buy multiple computers. And also note that when you are buying a new computer, you are buying all these four components. So your processing does not only double, it can increase by many folds. Okay, it can improve by many times, not only double. All right. So we talked about nitty-gritties of big data. Why do we require distributed computing to process big data? And now question is, why do we need to do it? We said that, okay, we had so much information we are storing, but why do we need to store so much information? We could just truncate it. Is it giving us any value? Okay. So there's a lot of value that comes from doing the big data analysis. There are a lot of, I mean, let's take few cases which are quite popular. Let's take a case of recommendation engine. Recommendation engine was the first and foremost use of big data in something very useful in case of Amazon. For so Amazon came up with this idea that, okay, if we start giving people recommendation, then it'll be great. They were able to do it because they had humongous data to churn. Okay, they had this humongous data which could, if churned, will give a great set of information about the user. Okay, and they build the recommendation based on the past history of various users, and it became quite useful, as in their maximum sales happen from the mailer that is being sent to the end user with the recommendations. Okay, so their maximum sales happen because of those mailers containing the recommendation, as well as from the website. From the website, the total the sales that happen due to recommendation, as in recommendation is in many forms on the website. First form is you may also like it. Second is people who bought this also bought that. Third is people who viewed this finally bought that. Those kind of recommendations actually make people buy their, I mean, discover new products and reach to a conclusion that this is what they require. Webber's question is that wouldn't network card be the bottleneck in distributed system? That's correct, Webber. But most of these solutions, say Hadoop and all, they have made sure that when you are doing computing, instead of transmitting data from the network, you transmit the code over to the network, so that because sending the code to the data is easier than bringing the data to the code. Okay, so most of these distributed systems make sure that they don't transfer the data, instead they transfer the code. Therefore network bandwidth, network bottleneck can be easily overcome. Okay, so Matthew's question is, what is metadata? So, what exactly is metadata? Metadata is a data over data. Is that your question, Matthew? Or are you trying to answer my question earlier? All right. So, these are the various use cases. I will go over these use cases one by one. So, first one, as I told you about the recommendation, there are many kind of recommendation. Customer who bought this also bought that, wear this with that. Then if you see, it's not only Amazon, others also have picked up. For example, in case of Netflix, there was this big grand challenge which Netflix has put in, where people had to build their algorithm for recommending the movies. It was very successful. So based on users behavior, people users past rating of various movies, giving the list of movies, or or in case of IMDb also the same thing is happening. Everybody is trying to give the recommendations, and those are very useful way. Suddenly suddenly the recommendations bring to the user a very good benefit of discovering, and taking the decisions. All right. And the recommendations generally used to happen over Hadoop in the following manner. So we had this brilliant tool called Mahat, which can basically take the input like this user likes this movie this much, and Mahat can immediately give you the recommendation like this user would like this movie this much. Okay, so off the self Mahat kind of tools which are part of the Hadoop system can give you the recommendation in a very easy fashion. All you have to do is prepare this three column data and prepare the ratings which is between 1 to 4, and Mahat will give you the recommendation. All right. So it's just a very, very, very vague, but yes. Nijesh's question is, but isn't recommender system an application of machine learning wherein big data Hadoop serves as data inputs? That's exactly correct, Nijesh. So when you run machine learning, what exactly is Mahat here? Mahat is a tool which has a lot of algorithms of machine learning, but it runs on big data solutions. Why? Because recommendations are useful only if the data is huge. Otherwise, if you have, say, 100 records, if you have, say, 100, 200 records, and you are having this brilliant algorithm which will give the recommendation, that algorithm will not give you the great result. Okay, no matter how clever is the algorithm, the uh, I mean, the data is far more important. The insights by a very dumb algorithm are better than a very clever algorithm if the dumb algorithm is performing on a bigger data. Okay, okay. I mean, if you have a very clever person looking at 10 records, he might come up with the insights immediately. Okay, if you have Sherlock Holmes looking at few data points and coming up with the whole mystery. Okay, but if there are huge number of points, it's easier to come up a better, it's a more stable way of solving problem. Therefore, machine learning, if done over the big data, is only the meaningful way to get the results. All right. Now, can you explain Mahat? Mahat is basically a library which runs on Hadoop, which has a collection of algorithm to do various kinds of clever things. Okay, and one of those clever things is recommendation. We'll go over this example step by step as a hands-on exercise, and we'll try to do the analysis. We will, in session number 7 or 8, we will discuss how exactly this is done. Here we are just trying to show you that this is called recommendation. Okay, here we are talking about user ID, movie ID. Had you been Amazon or somebody else, it could have been user ID and product ID. Okay, or it could have been something, some other features. Okay, but all it requires is this three column data. Nijesh's question is, so does it mean higher recall as well as precision? Yes, that's correct, Nijesh. All right. Now, the other very popular use case of big data, as in the use why we require big data, is the sentiment analysis. Sentiment analysis represents a problem of displaying or analyzing your public sentiment. How do people perceive your brand or your product? Okay, whether people are liking it, how many people are saying good things about it, how many people are saying bad things about it, and whether that ratio is increasing or decreasing. Ratio between good and bad is increasing or decreasing. So that is sentiment analysis. So you generally plot two graphs, one for bad, one for good, and over the time period. And you also mark various points in this graph when you start your campaigns. Say you have a brand, you launched a new campaign now, or you launched a new product. Okay, so that will be a vertical line in this graph. There'll be a vertical line in this graph. All right. So, all right. So there will be vertical lines on this graph in order to figure out whether our sentiment of our product is increasing due to a particular event or due to a launch of product. Okay. So, and this is very common technique. Now, how is it done? So you gather all kinds of data from all kind of sources, which means big data, I mean the volume and the variety, and you try to analyze it. Say, for example, you gather your Facebook likes, your Twitter handle followers, and you also gather how many people are clicking favorite in Twitter, how many people are retweeting, and how many people are writing comments. Now, when it comes to comments, that's where the whole problem starts. So, whether people are talking great thing about you or not, so you have various English sentences in English or any natural languages to analyze whether that sentence carries a negative connotation or a sentence means a positive thing for you. Okay, that's a very big challenge for the sentiment analysis. There are many ways to do it. First way, the easiest way is to just count the polarity of words in a sentence, and based on the polarity of the words you basically figure out whether a sentence is negative or positive. Okay, so each we have we generally keep a dictionary containing the polarity of each words, and we basically give a number to each sentence, and then based on that we analyze whether people are talking positive things about us or negative things about us. Similarly, another approach is the natural language processing approach, which is far more intensive. And in this approach, what we do is we take each of the tweet or each of the send comments on our Facebook or any other channels, and we analyze each comment whether the comment is just like we understand it. We use an NLP kind of tool to understand the full structure of the sentence. So as of today, there are really these brilliant techniques to do the parsing of the sentence using natural language processing and come up with whether a sentence is negative or positive with more surety. All right. All right. Nijesh says that have heard that Mahat's development support is stopped and people in big data are using MLlib over Spark. No. So there are Mahat guys are upgrading their algorithms. Okay. But for most of the time, Hadoop Mahat has been pretty good. And now also there are a lot of use cases for Mahat in various production environment. People are still using Mahat at a lot of places. They are just upgrading their algorithm so that it can run not only on Hadoop but also on other platforms. Okay. While MLlib has also come and it's pretty good, and we will cover a brief about Spark in this course. Okay. We'll cover around 2 to 3 hours of Spark in this, and that you will understand what do we mean by Spark and Mahat. Okay. Now, Nijesh's question is, can we use TF-IDF approach for sentiment analysis? We can discuss about it maybe off the in a separate thread. All right. All right. Now, so these were the two very common uses which we have all been doing. Then, other than these two common uses, there is something called search quality, whereby when people are searching for our data on our application, we try to improve the search results. Okay, so even if your application is a smaller data, say 100 GB or 200 GB, to give a billion search results, to give a billion search results, or to give a user a good set of recommendations, as in you, you did you mean this? Okay, so the spelling corrections, the word suggestions, the auto completion, and the in the order in which you are supposed to display the search results, all of these features of your search quality are hugely impacted if they are hugely improved if you utilize big data properly. For example, let's say you want to provide a great search engine which can give the correct answer even if user types various forms of say a word called blue dart. A user can type blue dart at least in 10-15 ways, right? Blue space dart, blue continuous dart, and they can basically write the wrong spelling for blue, right? And so to basically build a thesaurus, build a dictionary containing the similar words, you would have to gather a lot of data across maybe Wikipedia. You'll have to gather all the text and understand how, with what all names, a particular thing is represented. Okay, so for building a really good search engine, even if your actual data is in gigabytes, we would require building these building these auxiliary systems which might require a lot of big data processing. Okay, then there is something called A/B testing. All right, there is this A/B testing. So then I'll take your question after this slide. All right, I hope that's okay. And there is A/B testing. In case of A/B testing, we display a certain interface. Say there is a new version of your software, you display this new version only to selected few percentage of users, not selected but randomly selected few percentage of users. Okay, and then based on their feedback, whether, say for example, if Amazon has to launch a new color of their header, okay, if they are planning to change the header color, they will display that header only to very small subset of users. Okay, they'll randomly select a subset of users and they'll display them, and then they will observe for how long did the user stay on our website. Okay, and whether they bought or not, and then they compared this data with the users who are still using our older website. Now, based on this, did the user engagement improve, or did their buying tendencies improve? They will be able to figure that out. This is called A/B testing. A as in we were running version A of our website, and version B is being launched only to certain users to just understand whether version B is better than version A or not. Okay, and and that is how Amazon and these websites are able to able to do a lot of innovations without disrupting their services. Be it Google displays different kind of results and different kind of formats to different users. Okay, and just to understand whether a particular feature is improving or not improving, instead of few people sitting in a room deciding, let the data decide. They let the data decide, or they let the consumer behavior decide whether their product was good or bad. That is called A B testing. All right. Now, in telecommunication, there are lots and lots of use cases. I keep seeing it all the time. There is customer churn prevention, network performance optimization, CDR analysis, analyzing network prediction to network to predict failure. There are so many use cases of in case of telecommunication. All right. All right. Then there is big government, such as they use the big data for fraud detection, cybersecurity, welfare, the justice system, and healthcare and life sciences. Healthcare and life sciences, probably every problem which healthcare deals with is actually a big data problem. Okay, the starting with health information exchange, gene sequencing, healthcare improvements, and drug safety. There are lots and lots of use cases every day emerging which require you to process the data which is beyond one computer. Okay, the time of buying new supercomputers is gone because that same thing can be done in a very efficient manner using distributed computing. All right. Now, these are the various customers. It's a little older slide, but yeah, this it shows that who all are using Hadoop. I'm just taking Hadoop because quantifying big data customers is a very difficult thing. All right, and these are the common 11 myths. Okay, so we can let me answer Satyendra question and then we can take a break. Satyendra's question is: all these big data tools seem to be only used from Java. No, they can be used from various platforms. It just so happens that the tool which we are going to talk about today, Hadoop, is written in Java, which gives an impression that it can only be used from Java. Answer is no, it can be used. So the first recommender I may built was using Python. Okay. So and regarding Mahat is a command is has both the things. One on one hand there is an API which you can access in Java because Mahat is written in Java, but it can also be accessed using Python and other languages which has the binding for Java. And Mahat is a as a command line also. Okay. So Mahat is also a command line program which you can access from command line and get your work done. Okay, and that's how we built our recommender on Mahat a little while back, churning around 200 terabytes data in Python. Okay, so Matthew's question is which language is used more? In case of data analysis, what I have observed is Python is used more for a couple of reasons. First, there is a brilliant library. Second, it's quicker to start using Python for doing a little data hacking. Yes, yes, Nijesh. Mahat can work standalone if data is provided. When we say standalone, it's just a command line which is standalone, but underneath it is going to launch all of its work on Hadoop. Okay. Basically, it is going to run all of its algorithms in a parallel manner such that the whole cluster might be utilized. All right. Now, let's take a break of 10 minutes and come back at okay, let me write it. break back by 8:43 a.m. IST. All right. All right, so let's start. So we have a few questions before we move forward. Okay. Now, Satyan's question is there a stronger correlation between functional programming and big data processing? Mm, you can say, I mean, so first, object-oriented programming was not really a great design for number crunching or any data crunching, but and and therefore it's not mandatory for using object-oriented programming. But anyway, Python has all the features, whether it's functional programming or object-oriented, anything is. I think the bigger reason why people have started using Python kind of languages is because it is easier and quicker. Okay, and it's easier to use systems written in different programming languages in Python. So probably that's one of the reasons. Because take a case of SciPy. Is a very powerful library for scientific computation in Python. Similarly, NumPy is very good. That is one big reason why people have started using these languages. Yeah, and in a way, there is a relation between functional programming, specifically to the parallel computing, where we have to send one particular functions to be computed on multiple machines. You will understand it later on. So in a way, yes, there is a stronger correlation between functional programming and big data processing. Yeah. All right. Now, thank you, Nilesh. And all right. Now, Kiran's question is big data Hadoop only used for data analysis or batch job, or can it be used for user interaction? Example, what Facebook is storing data from millions of customers, millions of photos, text, videos, or likes every second can be viewed by user at present. Okay, if users are millions, is that big data? Okay, so yes. So his question in very simple words that is Hadoop, whatever we have talked about so far, suitable only for batch processing or analysis of the data? The answer is no. Okay, you have databases like HBase, which you can use to store the data in real time. Similarly, if you are building an application such as a video streaming, those kind of applications can be built such that the actual data is stored in Hadoop. Okay, we will understand it a little bit more when we go forward. Okay, so in case of a real-time application, such as if your date, if let's say, and there was one more question earlier, which says that I think I should take after I talk about Hadoop architecture. All right, so be with me, Kiran, and then we'll discuss it. Okay, there was one more question related to web applications. I think I should. So Matthew's question is, will we be studying Python in this course? The answer is no, Matthew. In this course, in the session number 3, session number 4 or 5, we will be going with Hadoop with Java. So a little bit of a Java refresher will be great, but it's not really mandatory because we'll be showing you how to use any other language such as shell programming with Hadoop, and that should be good enough. But if you are inclined for Java, we have provided we have provided one Java course along with the Java pre-recorded course along with the main course, which you can just quickly go through. All right. So, uh, Karupa Swami's question is, what about the OS for Hadoop? Okay. So as of today, Hadoop can run on Windows, Mac, and Unix and Linux. Okay. Because it was written in Java so that it can run anywhere. Okay, Karupa. So for example, something called HD Insights, which is from Microsoft, that runs on Microsoft's Windows cluster, is nothing but the Hortonworks Hadoop. Okay, Hadoop being sold and supported by a company called Hortonworks. They have released a version called HD Insights. Is It's for Windows. All right. Now, so these are the few common myths about big data. So first myth is about that the data has to be above or equal to in the range of terabytes. The answer is no. As I gave you an example of finding path in the map, even though the data was smaller, even the data was like in hundreds of gigabytes, still it would require it would require a distributed computing problem a system to solve your problem. Okay, therefore generally data is not the only criteria, but I mean in a way the only thing is the data has to be little bigger, not in kbs. Next is, it is always about social media, doesn't apply. No, it just so happens that people gathered most of the bigger data through social media or through the world wide web. But that does not mean that the need of big data is not there in other domains. Okay. Probably every domain as of today is intersecting with the big data. Will replace enterprise data warehouse? The answer is yes and no. Some of the enterprise data warehouse might move to Hadoop or might move to big data solutions, but not all. Reason being, E- EDW is great at handling the relational data, a data which has got strong relationships from one record to another, and in the transactions. Those things cannot be replaced with any of the distributed computing solution as of today. Okay, as of today, the enterprise data warehouses could be partly moved, not completely. You will understand it when we discussed when to use HBase, when to use this in a little bit more detail. Okay. Next is, it's just a buzzword, no practical applications. Every day I see new company adopting Hadoop and being successful. It's not it's not it's not what do you call? It's not a premature technology. It's not a buzzword. It's a fairly successful uh, suite of components, and also most of the time a company does not have an alternative to big data. Okay, people try to launch their supercomputers, they try to buy really high end solutions, but at the end of after a few months they all realize that that is not going to solve their problem, and then they have to move to big data anyway, meaning a distributed computing environment. Fifth is new concept. No, as I was telling you, even in 2002, when I was working at DE Shaw, we had a 10,000 node cluster, and we did a very good job at managing huge data as well as doing the computing on the huge data. Will be the future? No, it is the present. Is expensive? No. Almost every tool in in big data suite is open source. All the tools which we'll discuss as part of this course are open source and are better than any of the commercial tools. Okay, so I mean, I have seen even inside Amazon, we discarding our own components in favor of open source, up in favor of the component that are lying under umbrella of Hadoop. Okay, so as of today, these open source components are very stable and good, and are most of them free to use even for the commercial use. Okay, the only thing that is expensive is the people as of today, because there are only few people who has this great experience, but 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 that too is improving now. Okay, is only for data scientists or is a magic? No, most of the algorithms that is designed by data scientists is actually publicly available for use. We have enough hardware, we do not need any more. That's another myth. Big data solutions do not require special hardware. That is the main quality of a big data solution, because they should be connecting the existing hardware in a network and making the use of it, right? And therefore you don't need to buy new hardware. Next is, we will build it when we need it. This is probably the most fatal syndrome I see in case of industry. What they believe is that it's something like a plug and play. Okay, but what they do not have are yet to understand what they are yet to understand is that if tomorrow you come up with this great idea of providing your customer a better experience or acquire more customers, and that depends on the data, and if you did not store this data, tomorrow you will not be able to just get the data back. Okay, therefore you cannot build it when you need it. You have to plan now to in order to start storing the historical information, the valuable historical information about your users, about your product, and the general industry pattern. So, and to do that you will have to have a big data solution. Okay, next is, uh, we will okay, big data is about Hadoop? No, big data is not about Hadoop. There are many technologies which lie under the purview of Hadoop, but Hadoop seems to be the most complete one and most welcoming to other components. Okay, for example, Apache Spark, which was launched recently, is adopted under the umbrella of Hadoop, and I mean, the new component such as Spark was able to fit into the ecosystem quickly. Therefore, although big data is not about Hadoop, it just so happens that Hadoop seems to be the most complete ecosystem as of today. All right. The salary trends and all, you can clearly see. This one I have gathered from Indeed.com. You can also just go through it and you will realize that Hadoop has got a great salaries. And the salary trends is anyway better than almost every other technology. And the other big data solutions are, as I was telling you, that big data is not only about Hadoop. Okay, the big data solutions also include Cassandra. Spark is anyway now part of Hadoop. Cassandra, MongoDB, Google Compute Engine, and Hadoop. These are just few choices. Cassandra and MongoDB are databases which also provide you some amount of computing in the form of MapReduce and other constructs. While Spark as a standalone does not provide you a storage, it only provides you the processing. While Google Compute Engine is a hosted environment, is basically software as a service or software as a platform, and we basically use their systems from after uploading our data onto their systems. But that may not be acceptable for lots of organizations. Therefore, generally, the most complete solution we generally have is the Hadoop. And Hadoop is provided by multiple companies, including IBM. So, though Hadoop is open source, but there are many implementers, including Hortonworks and Cloudera, MapR, Qubole, and IBM, Microsoft. Okay, so all of them are basically providing their own slight deviation from Hadoop, as in they add one or two more components into Hadoop ecosystem along with their installer, and that's what they call their own version of Hadoop. Okay, all right. Coming back to what we have here. All right, let me just go through this slide and yeah, and then we will discuss your question. There are very important questions. All right, so or I think let me just cover your questions first. Let me just cover your questions. Okay, so the question is, does Hortonwork manage the huge hardware setup for Hadoop? No, they don't. They provide the solution. So Hadoop is implemented by multiple companies, as I was telling you, but and Hortonworks is one of those. Hortonworks does not manage the huge hardware setup for Hadoop. They basically are implementers, as well as they provide you full technical support on the software. Satyan's question is, if time permits, can you touch on the data scientist part again? And isn't that the data scientist is ultimate user of big data? Okay, so let's. His question is, who exactly is data scientist? Is he the only user of big data, or who? Okay, so data scientist is someone who understands programming, who understands statistics and maths, and who understands the business. Okay, the domain, maths, and programming. Okay, a data scientist is someone who has these three abilities. Now, but in the industry, we keep on seeing it all the time that everybody seems to be the data scientist. And I have seen even a lot of data scientists who hasn't gone beyond few hundred records, okay, or maybe who hasn't gone beyond 100,000 records when they process the data. Okay, so there are the full range of people in the industry with different backgrounds, and in general, a data scientist has got these three experiences: maths, and domain. Okay, it doesn't have much to do with the data scientist, but if data scientist goes through, understands big data, then they can derive really better results. Okay, now Kunal's question is, have you seen any on-premise solution running on Hadoop? There are many on-premise. Lots of people run Hadoop on-premise only. On-premise as in inside an organization, people are running Hadoop. Yes, there are lots and lots of people who run their own Hadoop installations. Anandita's question is, are Netezza and Teradata also different versions of Hadoop? No, they are different solutions altogether. Or you can say they are mainly the competitors of Hadoop. Okay. Now, Satyan's question is it right to compare Hadoop and MongoDB? I believe one is more about processing and MongoDB is about NoSQL storage. Okay. So, I would say that Hadoop is not only one component. Hadoop is a full ecosystem, as we will see further. Okay. And we cannot compare HDFS with MongoDB either. All right. All right. So Nijesh's question is Elastic MapReduce from Amazon competing with Hadoop MapReduce? So Elastic MapReduce from Amazon has got the same construct as normal Hadoop MapReduce. Okay. So it's not competing. It's just one is for the people who don't have hardware or who don't want to manage hardware. Amazon one is the one where you don't want to buy hardware, and those people who have their own hardware and can manage the hardware, they go for their local versions. Okay. So it's not competing, it's just complementing. All right. Okay. So Anandita is saying, I have heard the Netezza and Teradata used Hadoop ecosystem and build their platform. So Netezza and Teradata is actually independent solution. I'm not sure how exactly are they using it, using Hadoop. Maybe they have ported part of their solutions onto Hadoop. I might have to take a look at it. All right. Now let's come back to our our discussion on Hadoop. Okay. So there was one person called Dog Cutting and Mike Caffarella. They were basically trying to build their personal uh, as a personal project. They were trying to build Nudge search engine. They called their search engine as Nudge. And that's they when they were trying to build it and crawl the internet, they hit the bottleneck where they realized that they won't be able to store too much of data reliably, neither they will be able to do computing using their existing technology stack. Okay. And they at the same time when they got stuck, luckily Google published all the three papers of their components. The first paper they published was Google File System. And what did Google File System do? It provided the storage of the data on the whole cluster. If you have a big cluster, then Google File System provided you that. Okay. Now, second thing which Google File System provided was Google MapReduce. And good thing about Google MapReduce was that it could do the calculation on the whole data which is located in Google file system. The third paper which Google published was Google Big Table, which was like a database, which has rows and columns, and you can store the data in rows and columns, and you can edit a particular cell, you can edit the row, you can edit a column, you can edit one full record, and so on. So these three papers came from Google at the same time when Dog Cutting and Mike Cavrella was stuck building Nudge search engine. So instead of finishing that search engine, they basically took those papers and implemented that paper, and that is what is known as Hadoop as of today. And the name of Hadoop comes from the toy elephant. It comes from the Hadoop. It was a toy with which Dog Cutting's son was playing, and the something which is most important when we talk about Hadoop and what it is it that differentiate Hadoop from every other is the open source. Had Hadoop been had not been open source, had it been closed source, there could have been no adoption at all. Nobody could have actually used it. Okay. Since all these data intensive technologies lock in the data into their own platforms, if they are not open source, people would not use them. Nobody would like to lock in their data and then, you know, and then being able to recover it. Okay, in case the company shuts down. Therefore, being open source has been the most important thing about about Hadoop. Next thing is was it was powerful, it was popular, and it got a humongous support from the whole community. It is a framework to handle big data, and when we say big data in terms of Hadoop, their definition is reliable, scalable, and distributed computing is called big data processing. Okay, so every component that is under the Hadoop has to have these three properties. It should be reliable, meaning in case some machines fail, in case some components fail, it should recover from those failures. Second, every component that is lying under the umbrella of Hadoop should be scalable, meaning today we are running this component on 10 computers. Tomorrow we have to run on 20. It should not be a problem. Third, it should be for distributed computing, meaning, which is obvious because distributed computing means that it should run on multiple computers simultaneously. All right. And most of the components in Hadoop are written in Java. Okay, but the new components which Hadoop is adopting are not necessarily written in Java. It so happens that in the initial time, HDFS, Google MapReduce, and MapReduce and HBase, all of the main components of Hadoop are written in Java. All right. So this is about the basic of Hadoop. So let me just take you through the stack. Okay. Let me just take you through the stack. And other than this whole stack, we will also cover Zookeeper, which is not mentioned here. After launching our course, we realized that Zookeeper is also quite important. So we included Zookeeper also. And we have expanded our Spark course so that everybody understands what exactly does Spark do. Okay, we'll do a full hands-on with all of these technologies here in our course. So but before going forward, let's understand what does it mean. So the most important component is HDFS, Hadoop Distributed File System, a file system which stores its folders and files on multiple computers without user having to bother about it. Without user having to bother about it, uh, HDFS internally stores all of its data on multiple computers and multiple hard disks. Okay. Now, HDFS is one thing which basically is the backbone of whole Hadoop, okay, on which everything else depends. Now, on top of HDFS, as I was telling you that we take the code and execute it near to the data, that kind of execution is done using Yarn. Okay, Yarn is a sort of an operating backbone of this ecosystem to which we can tell that, hey, can you get this particular work done on these computers? Okay, and keep on trying it, and whenever, I mean, in case one fails, try it somewhere else. So Yarn is sort of the backbone of computing. Whenever we want something to be executed, we use Yarn. So also please note that as a we do not directly interact with Yarn unless we are developing a component like MapReduce or Spark or something else. We do not interact with Yarn. As a user of Hadoop, we do not interact with Yarn directly. Instead, we interact with Yarn through the component like MapReduce, Apache Spark. MapReduce, Apache Spark are one way of getting the computation, are two ways of doing the computation done over Yarn on our data which is lying in HDFS. All right. So MapReduce, Spark, and Yarn are for computation. Now comes the database. HBase is the database. This you can see here. It's a NoSQL database in the sense that it does not provide you the great transaction kind of thing of relational databases. Neither does it provide you referential integrity kind of checks. And you will understand it. Why doesn't it provide it when we discuss further in session number 6. So HBase is a sort of a database which stores its data in HDFS, and to churn the data to basically query the data on HBase, we use MapReduce to churn the data. Okay. Next is, on top of this, an HBase does not provide directly an SQL query to query the data. Okay. Instead, you use a tool like Hive to query the data from HBase or HDFS. Next kind of tool which is similar to, so Hive is basically a query tool because you cannot keep on writing the program for each and every query. So if you have to query anything in the network, so so either you can write the code which is in MapReduce, or you can write the code for Spark to query the data from the HDFS, or you could use a tool like Hive to which you will give your SQL query, and it will convert that SQL query into MapReduce. Similarly, there is another tool called Piglatin. Piglatin also does a similar job like Hive. The only difference is Piglatin is itself a different language which is very similar to SQL but designed from bottom up for distributed computing, because SQL was not really designed for distributed computing. Okay, so you have got a place to store data, a way to churn data in files. Similarly, in HBase, you can store records. HBase is great when you have to edit a lot of data, update records all the time. Specifically, when you are running a web application. So somebody was asking, if I'm a web application developer, would this mean anything to me? Answer is yes. And first and most important use case is learning to understand the HBase. Okay. So HBase database runs on multiple machines and stores its data underneath data into files in HDFS. And it's great when you have billions of columns and billions of rows. If you have millions of columns and billions of rows, HBase is just wonderful. It is very fast and it can handle a lot of load. Okay, so whenever you have to edit the data really fast, or you have to access the things record wise, then HBase can be your great solution. Similarly, but to churn the data from HBase, you cannot keep writing MapReduce all the time. Therefore, there is something called Hive. There's something called Piglatin. Piglatin and Hive are very similar to each other. Just that Piglatin is great for churning the data which is not in tabular format. While Hive, because it's designed on SQL, it wants you to first create a SQL table and then churn the data. Now, third is Mahout. Mahout is great in the sense that it's a machine learning library. Okay, it contains the set of functions which can be used out of the box rather than you having to understand the algorithm and start using them. Now, on Mahout used to run on MapReduce. For Spark, we have similar tools like Hive. We have Spark SQL. Okay, so while Hive and Piglatin run on top of MapReduce, Spark SQL runs on top of Spark, and there are newer tools like Spark R, which run on top of Spark, not top of MapReduce. So so these tools help you derive interesting analytics on top of your data. Okay, now if you okay now there's something called flume at the bottom of the diagram. Now, if you have a lot of unstructured data in your network, and that and that data you are pushing to you have to push to HDFS, then you can use Flume. Flume is really, really powerful and great for pushing the data from across the network, be it your Apache web servers, be it your movie files being generated in a folder, or be it whatever. Flume can be used as a pipeline to push all of your unstructured data into HDFS. Specifically, if your data is getting generated continuously. If your data is getting generated continuously, then you can use Flume for moving that continuously generated unstructured data onto HDFS. Okay. Now there is something called Scoop. Scoop has been designed to move your existing SQL data or relational data to the HDFS or HBase or Hive. Okay, Scoop helps you do that to move your data to HDFS or HBase, as well as once you are done with running Mahout, for example, and you got this data in nice format, you can move the data back from your HBase, Hive, or HDFS into Scoop. Okay, so basically, Scoop and Flume are data movement tools, but they are not really ETL tools. Okay, keep that in mind. ETL is mostly done using Piglatin or Hive, or maybe using MapReduce. So Nijesi's question is, did not get the point that HBase is a database which stores data in HDFS. Yeah. So it's like saying you have got MySQL. What does MySQL do? You store records, you manipulate records, as in rows and columns and cells. You say update this, update that, delete this, delete that. And then indirectly, MySQL stores its file into the normal file system. In the similar way, HBase provides you a store in which you can edit each cell, as in update the row, update the column, update each I mean individual cells, or delete a row, delete a column, and so on. So HBase provides you that, but at the end of day, it stores the file generated that contains all the records into the HDFS. All right. I hope you got the point now. Also, keep that in mind. This is a common confusion that why do we have HBase when we have HDFS? So it's like saying that when we have normal C colon D colon, why do we require MySQL? Or why do we require Oracle? Why do we require MS SQL? Okay. So Matthew's question is HBase an actual database, or does sort of coordinate between many databases like SQL and NoSQL? No. HBase is sort of a storage, is a NoSQL storage in which it has its own way of storing records, and that's basically what do you call a large table, and yeah. So it's actually a actual database which can store billions of rows and billions of columns. That is something you may not have heard before. In case of relational databases, it's not really a great idea to have many columns. Or all right, all right. Now there are a few more questions. These are interesting questions. Will HBase have unstructured data also? Deepak's question is, will HBase have unstructured data also? So HBase would have kind of a semi-structured data. Okay. But each individual cell, the way you, when you have dealt with the SQL, you can store string, you can store date, you can store time, you can store number, you can store decimal number into that relational database. But in case of HBase, in each individual cell, you can store any binary data. Okay, you can store any binary data of any size. All right. Therefore, in a way, if you look at it, each individual cell can contain data which is completely unstructured. Nijesi's question is, can HBase be replaced by MongoDB or Cassandra? Yes. Cassandra and HBase are head-on competitors, just that Cassandra doesn't do a great job storing its data into the HDFS file system. Similarly, MongoDB also is not greatly efficient when we try to store MongoDB's files onto HDFS. So Leonard's question is, would you ever use Hive to run queries against HBase? Yes, we do. Okay. So Ganeshan's question is, I could not able to get the process of yarn. What role does it play? So the kind of role as of today yarn is playing is that of an operating system. We have our program written in Java, written in XYZ platform, and this and that. And then once we have this, we ask operating system to execute it. Now it is up to operating system or a virtual machine or basically this operating layer that it should execute my task. Okay, that's exactly the role of yarn when it comes to a distributed processing. So in case of our normal operating system, it runs on one computer, while yarn runs on the whole network. Leonid's question is, how would that be different from using Hive against uh, Hadoop differently? Let me understand. Yeah, so the way we can query the files lying in HDFS, okay, similarly, we can use Hive to query the data lying in HBase, okay, using, okay, so, all right. So the way when we are using Hive, we use H catalog. So similarly, when we are using Hive with HBase, we will be talking to HBase, though we'll be using H catalog, but we'll also be talking to HBase in order to query the tables. All right. Web's question is, can Flume and Scoop exist together if there is a mix of structured and unstructured data? Okay. How does system decide when to use Flume and when to use Scoop? So it's not system that will decide about Flume and Scoop. They look like very close brothers, but their behavior is fairly different. Okay. On one hand, Flume is a pipelining system. Flume has got services which run on one machine and another machine. They keep on transmitting data from one place to another by the way of multiple Flume nodes. Okay. On other hand, you have Scoop, which is nothing but a simple plain command line, which you tell that this is my database, this is my table, and these are the columns which I'm trying to copy from from this database into this HDFS file or HBase. Okay, so using a scoop, you can move to and fro the data between HBase and the and this database, or HDFS and this database, and so on. Okay, this is a simple command line, and you would wonder that why would you require scoop? You could quickly write the same thing using your MapReduce. But after some time, you'll realize that yes, it does play a role in getting the work done of import using multiple computers simultaneously. All right. So Nijesh's question is HDFS a kind of a redundant fault tolerant system? Yes. So we'll talk about this. I think it's a time to move forward. We have okay. Now Sushil's question is Flume and Scoop are software to put data into HDFS, while HBase is okay. Flume and Scoop are softwares to put data from external world into the HDFS HBase. Okay, and okay. So, Weber, was I able to answer your question? So it is we who has to decide. System will not automatically decide which one to use, Flume or Scoop. Okay, and we'll have to. It will be we who will trigger it. Okay, and yes, in a way you're correct that we'll have to use a mix of both based on our problem statement. All right. Okay, so we have Sushil's question. So yes, Flume and Scoop are a way to put the data into HDFS. That is correct. But uh, HBase is not a merely way of accessing HDFS because we can directly access HDFS. So when we have to store the data in, say, there is a data in full files, we just want to store that full file, right? But in case you just want to deal with big files and you want to, in that case you will use HDFS directly. But in case you want to say delete this record, update this record, insert this cell value, and so on, in those cases we will use HBase. Okay. So Matthew's question is, so the HDFS gathers information between HBase and other database? No. So HBase, just a second. Okay. So HDFS gathers the information between HBase and other database. Um, no. HBase is a mere storage for everybody. Okay. You can store the files. Whether it's HBase or some other database, they can all store their data into HDFS. Now, Weber's question is, how about semi-structured data? In those cases, if the data is in files that you can use Flume to move the data into HDFS, then your MapReduce tasks, Pigletin tasks, or Hive tasks can clean the data, form the structure out of it. Okay. Is querying from HBase faster than HDFS? Yes, that is correct, Nijesh. So in a way, updating the record and querying the data using HBase is faster than what it is through HDFS. So Cecile's question is, I didn't get about Mahout. Mahout is a collection of library which basically runs on top of Yarn and utilizes the information, utilizes the little bit data churned by Pig and Hive to generate the insights. Okay. Now, next question from Sushil is, what is the role here and why we have horizontal relation between Hive and Pig? Horizontal relation between Hive and Pig is that they are sort of competitors to each other. They are not dependent on each other. All right, Sushil? Great. Now, Kunal's question is when to use Hive and when to use Spark SQL. Okay, so when you want to do your processing through MapReduce, you use Hive, and when you want to do your processing through Spark, then you use Spark SQL. Okay. Now a bigger question would come as when to use MapReduce and when to use Spark. The answer is that most of the computing which you want in real time that you can do on Spark, but in case you don't want your memory to be completely consumed by Spark, in those cases MapReduce would be a better job. So Nijesh's question is, Pig seems to be more concise and easier. Will it replace Hive? Um, I don't think so because Pig Latin, though it's a simpler language, all my students in past have started preferring Pig Latin over normal SQL. But still, there are lot many users who have their stored procedures, their SQL queries written in SQL. They will still be using Hive. Okay. Now let's take a case of. All right. There are a few more questions. So Kunal's question is, as we can store RDD in cache, so do we really need to load in data warehouse or in memory DB? So it all depends on what kind of throughput are you expecting. If your throughput requirement is below 1 second, you go with the in-memory DB. Otherwise, you will be okay with using a Spark. All right. And okay, so let's take a case of doing a recommendation. Okay, let's take my case of doing the recommendation. We were keeping the track of which user accessed which page, and we wanted to give them the recommendation. So what we did was we took all the logs of from our Apache, and based on that log, we we basically based on that log we cleaned it up and we formed three column, uh, you can say three column data. First column was user ID, which we had internal user ID, and which page they visited or which product they visited, how many times. So we normalized it and we formed the ratings just like movie ratings, user ID, product ID, and the rating. As in, rating is derived from the how many times a user has visited one particular product. And based on that, we were able to figure out this user likes this product this much, and so on. And we gave that to Mahat and we did the processing. Now, if you see, when you do these kind of things, you have whenever you are doing such kind of processing, you will have multiple level of multiple components used in the project. Therefore, you will have to tie them together, meaning first copy the data into HDFS, then do this, then do that, and so on, right? And at the end of it, you run Mahat, and once you have run Mahat, whatever is the result of Mahat, whatever are the recommendations, move it to your web application and display it there. Now there are many things you have to do here, right? If you keep on doing it manually every day, it will be it will be error prone, it will be waste of time, and it will be slow. Therefore, therefore, you use a tool like Oozie. Oozie is like your Maven and or make kind of a XML script where you specify that do this, do this, do this, and that's it. Okay, that's about Oozie. And you can interact with all of these components from command line, Java, or Python, or from the web interface. Nijesh's question is Spark distributed and scalable method? What we saw with Memcached, which Facebook uses. So Spark is far more scalable than Memcached and other systems. So yes, Neha, we are on the timeline. So we have 20 more minutes. Okay. All right. So okay. So if you want to have a look at the console, you can have a look at the console, those who have already enrolled, and you can also have a look at Hue, and you can also log into SSH onto our server, and yeah. So we will cover all of these details in tomorrow's class on how to use it. Okay, now let's. Okay, so come again. Let me just see if you have any more questions. All right, should we move on to one more topic of uh, the HDFS? I think we can cover that. We still have around 20 minutes. Okay. Otherwise, we will cover everything in the tomorrow's class. Nevertheless, all right. So let's start with the HDFS part now. Okay. No worries, I'll not hurry up. I'll just focus on your questions because if something is not covered, we can always extend one more class. That's not an issue, but questions need to be answered. All right. My agenda is not to hurry up to cover everything. Okay. Same timing, Sushil. The tomorrow's class will be from 7 to 10 a.m. IST. Okay. And for tomorrow's class, Neha, you'll have to enroll in the course. It is up to you. If you are liking the course, you can enroll for the course. All right. So, okay, all the details are available on our website, knowbigdata.com, and have a look at it. All right. Yeah. This today's session is generally open to everyone. Uh, okay. And it's very important to answer everyone's question. All right. So feel free to ask questions. There's no hurry in it. All right. All right. Yes. So, okay. So for tomorrow's class, if you want to attend, you can enroll, and that's it. All right, great. So the main component which we talked about is HDFS. So we want to understand what exactly HDFS does. So, but before that, I would like to ask you a simple question. If you have planned that you are going to store 100 terabytes of movies, how would you go about it? Imagine that you are living in a hostel and all of you planned that, hey, let's build our local movie storage so that every one of us can store movies in that and also watch the movies whenever we want. And your estimate says that you will require around 100 terabytes of space. Now, how would you go about building such a storage? Okay, feel free to come up with your own solutions. The the more solutions do you come up with, the better it would get. Okay. All right. So Matthew says that how many external hard drives? It is up to you. It's your call. You have to give me the capacity planning. What all do you want to use? Nijay says that 10 different accounts on the Dropbox will be enough. So, okay, that means, okay, so every time you have to watch a movie, you will have to download the movie from Dropbox. Correct? And Nijesh, we are talking about 100 terabytes, not 10 terabytes. Okay, okay. Webber says multiple computers over the local area networks, movies in chronological order on different machine, brilliant. Sushil says distribute in 100 systems and have layer on top of it. Good. All right. Kunal says on a distributed network for sure. That's correct. Anandita says external hard drive. Yes. How many hard drives, Anandita? Neha says that we will use a cloud-based platform. Yes, go ahead in the details. I want to see the details. Satyan says that please do suggest some book to read big data in general and Hadoop to be specific. Okay, so okay, I'll just once after this we can discuss all of it. Okay, so the for books I prefer the definitive guide to Hadoop as well as the wiki from Apache is actually pretty good. Now, Kunal's suggestion was to have distribute it on the network and create a lookup table in the memory. Good. Okay. Satan says use Oracle 12c. We can use hypervisor over 5 different machines in our hostel. Good to multiply it to 10 virtual machines. Okay. 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 Matthew says use 4 hard drives, each of 30 terabytes. Okay. All right, all right. So, okay, so almost everybody has given a suggestion like this. So the way we had always built, like the way Webber has suggested, Matthew has suggested, and other persons have suggested, the way we have traditionally built such kind of storage. Even for that matter, I was discussing with few people at national laboratories. I mean the laboratories for NASA, though they still have this kind of structure for some data. Okay, now this is a classic way of doing it. So what you do is you buy 100 hard disks, place it in multiple computers, connect these multiple computers in the network, and mount these hard disks or map these hard disks onto one particular computer's folders. Okay, or multiple computers folders, and then inform everybody that access this computer to access the all hard disks, or access these computers to access any of these computers to access this hard disk. Okay, now what is the problems do you see here? Do you see any problems with this approach? You have got basically you attached 100 hard disk onto multiple computers, then you map these hard disk in a folder such that they look like subfolders to a parent folder. Okay, and then we can put year wise. Weber was saying you put it year wise, as in chronological, as in all the movies of 1930s go into drive number one, all the movies afterwards 1940 and so on go in different drives. Now my question is, do you see any problems with that? Or you could say that all the movies starting with A go into drive 1, all the movies starting with B go into drive 2, and so on. Now, do you see any problems with this? Correct. So it takes time to gather the data. That's correct. Duplicate movies. Okay. If you have same file distributed in many folders. Okay. Okay. If you have a really big file, then you might have to, yeah. Yes, Nijay says high latency time for querying, brilliant. Keep going. All right. There are many problems associated. Some of you already have covered. First is, what about failovers, and backup? In case one hard disk fails, do we have a backup? And traditionally, what we did was we installed something called redundant drives, RAID, RAID. Okay, what does that mean? That on each computer, we will have the backup of each hard disk. Now, the problem with that approach is in case one computer dies, then both the hard disks will be unavailable, right? Therefore, in this system, it's very difficult to have a failover and backup. Next is, how would you distribute the data uniformly? Even if year-wise we try to store, we start with 1930. In 1930s, there were only few movies, and then 1940s and so on. But and therefore, the data may not be distributed uniformly. Secondly, in case the most recent movies, the 3D ones, are bigger, they may not fit into one particular computer, right? So therefore, we will not be able to distribute the data uniformly. Third is this the best value for money? And what about increasing accessibility? In case everybody wants to watch a particular movie, it's Independence Day, everybody wants to watch Saving Private Ryan, right? Therefore, the computer having the Saving Private Ryan will die out of overload, or the disk which is having that Saving Private Ryan will be overloaded because it's a physical movement of the header which reads the movie for you, right? Therefore, it can only read one movie at a time. Now, scaling out. Today, we had a requirement of 100 terabytes. Tomorrow, we might have a requirement of 200 terabytes. Now, in those cases, what are we going to do? Is it easy to scale out? Can we add 100 more hard disks easily and then connect it somehow? Or redistribute the files? So will that be automatic? Will that be easy? Right? Therefore, when you have such kind of requirement, you generally go for HDFS. And the main reason for going for HDFS is the following. HDFS is made up of two kind of systems. One is called admin node and other is called data nodes. The way we had to keep a plan that all the movies start for this year is on this machine. So this is metadata, this is data over data. This between mapping of which movie is on which machine, this kind of data is called metadata, and this metadata is stored in admin node. So admin node keeps track of which file is where, while data nodes store the actual data, actual files, actual content of the file is stored in data nodes, while the full file while the full information about the file is available at admin node. Admin node does not store the actual data. Okay, and all of these, whether data node, admin node, all of these are basically services which run in the network, listening on a port and answering to you, just like a web server which is listening to your HTTP queries on 80 ports. Similarly, these data nodes or admin node, they are services running on multiple machines. They are not really hardware, which means you can run data node and admin node on the same machine. You can even try to force, you can even force multiple data node to run on the same machine, but that doesn't make any sense. So you have two kinds of node. One is called admin node, that is singular, which is sort of an index of what is where. Okay, and then there is a data node that store the actual files, actual content of the file. So whenever we say ls to HDFS, say give me the list of files, it does not go to data node, it basically goes to admin node and displays you what are the files located in a folder. Reason being, the list of files is the information over the actual data, and that is stored in the name node. Okay, so that's what is the role of admin node, and actually that's the role of data nodes. Now, the admin node stores all of this metadata into the memory. Okay, why it stores the metadata into the memory? Because it should not take time to retrieve the information about the files. Inside, the another important information for all of you is, when we are storing a file, metadata goes into name node, the actual data goes into data node, but the file gets sliced into pieces of 128 MB that are stored across multiple data nodes. Okay, and the size of each piece is 128 MB. The last piece is smaller than 128 MB generally, because not everything is a multiple of 128 MB. So if you have 138 MB file, you will have one file, one block of 128 MB and a second block of 2 MB. All right. Now this splitting of file is a very important architectural decision of HDFS. It helps you fitting big files into small disks. It leaves less unused space onto the disk. It optimizes the transfer. It optimizes the transfer of the data. Okay, because if you are planning to watch just the beginning of the movie, you can go to the first node, and in the middle you can switch to the second node, and so on. Because if there is a big file, let's say 1 GB file, 1 GB file will be broken down into 8 blocks. And if you have 8 nodes in your network, this file will maybe stored on 8 different computers. That means when you watch the whole movie, you will be talking to 8 different nodes at different point of time. You will read the first 10 minutes from one machine, next 10 minutes from another, and so on. That way, you basically utilized 8 different computers instead of overloading only one computer. Correct? So that way, it optimizes the transfer of the data. Also, it also distributes the load to different machines. All right. Now, where does data node actually store that block file? Internally, data node is basically storing that block, that 128 MB block, into the local file system as a normal file. If you go into each data node and go to the place where it's storing those blocks, you will see these big files, these files with the big random names, and each of them will look like will be like a normal file, just that their sizes would be 128 MB. All right. I think, Matthew, does that answer your question? All right. Now going forward, each of the data node, each of the block that has been copied to a data node has got multiple copies. Meaning, if we are storing, if we have if we have one file of one block, right, it'll have 3 copies, and these 3 copies will be on 3 different data nodes. No 2 copies will be on the same node. Why? Because in case one data node goes down or two data node goes down, immediately the data from the third one will will be used in order to bring up the replica copies again to 3. So by default, the block size is 128 MB and replication factor is 3. Both of these parameters can be changed. Okay. So you can change the replication factor from 3 to 2 or to 1 or to more than 3. If you are increasing the replication factor to more than data nodes, that means it'll give you a warning saying that your file is under replicated, because it will not put two copies of the same block on the same machine. So it does not make sense to have more replication factor than the actual number of data nodes. So replication factor dictates how many copies are going to be there of each block of the file. Okay, so in case one data node fails, the lost blocks will be recovered from another replication fact and another replica, and the replication factor will be brought up to whatever was promised, right? So that way, even if two data nodes go down, still nothing will get lost. There'll be third copy always. And immediately, as soon as the data node goes down, it does not require any manual intervention to bring up the replication factor to a certain level. It automatically happens at the HDFS layer. Immediately, the data nodes are instructed by name node saying, can you recover your data from this to this? Can you make a replication of this file to this place? And data nodes start communicating amongst each other and get the work done. Now, a common syndrome here is that when the user comes to name node, this is a psychology which we have. The user will be all the communication will be happening through name node, and effectively name node will become the bottleneck. No, this is not the way HDFS communicates. Instead, HDFS communicate like this. The user uses something called a command line called HDFS command line, or client or a driver. And so user asks the driver, can you get me this file? And the driver goes to the name node saying, can you get me this file? Name node, instead of getting the file, it tells the client driver that go get it done by yourself. Do not bother me. Here are the block names. Here are the data nodes on which these blocks are lying. Just go and get it and assemble it, because these are the parts, right? These are the blocks. So assemble it and give it back to the user. Similarly, when the user is trying to write the file, okay, let's say user is trying to write the 1 GB file. So it tells the client driver that can you just store this file on the HDFS. Driver takes the file, splits it into blocks, tells name node that it wants to store this file. Name node tells that break it into blocks and store the blocks on the data nodes. And this is the list of data nodes where you can store it. And once you are done with the storage, please let me know. This way, name node has avoided to become the bottleneck. Name node got itself out of the way of being stored, being the bottleneck, right? And client driver will parallelly talk to 8 different data nodes and try to write all 8 blocks parallelly onto the data nodes. This way, the overall efficiency of writing is actually improved. And the replication, meaning copying, making the duplicate copies of the block happen amongst these data nodes eh, automatically. Okay, also client driver makes sure that a lot of optimization happen on time. For example, the first copy is generally stored on the local data node. If the user is standing on the data node itself, then the first copy is stored on that data node, and that data node transfers the whole data to other data nodes. Okay, there are a lot of optimizations which are done. Also, as you might see, that name node looks like a bottleneck, but there is something called secondary name node, which takes care of all the all the backup of name node. So anything which is written into name node by client driver, same thing is written into the secondary name node by the client driver. Similarly, everything that data node informs to name node, data node also informs the same thing to the secondary name node. So secondary name node remains as a cold backup, which is having exactly same data as name node. All right. So therefore, if name node shuts down, you can quickly switch it to the, or it will automatically switch to the secondary name node. All right. So Nijesh's question is how many redundancy cycles are there? I did not get the redundancy cycles because here each block is copied thrice. There are three copies of each block. Okay. Okay, considering the replication factor, I'm reading the question from Nijesh. Considering the replication factor is 3 as the data grows, how will Hadoop hardware system manage the requirement of data node? So data node is something which you will add. Okay, there is only a couple of independent vendors such as Qbol who provide you this kind of HDFS, which has the elastic expansion, as in when you have more requests coming in, more data nodes are added automatically. All right, but by default, it's not there. So Kiran's question is where we get this. You will get this recorded session in an email. Okay, considering the replication factor is 3, as the data grows, how will the Hadoop hardware system manage the requirement of data nodes? Considering the replication factor is 3, okay, as the data grows, how will Hadoop hardware system manage? Yeah, okay. Now Kunal's question is, if one node goes down and comes back, then what happens? All right, so yes, that's a very good question, Kunal. So if one data node goes down, now the replication will start happening from other nodes to other nodes, so that whatever was lost as part of that data node going down gets recovered automatically, right? Now question is, what happens in case the data node comes back again? So again, it will figure out that okay, these are the older files on this node, these are the newer files on this node, and it will automatically will synchronize its file system from the latest version through name node. All right. If failed data, okay, so I hope I answered the question, Vaibhav and Kunal. So in case there are more copies, so the same copy is there already, it'll just drop one copy. Okay, it'll just drop one copy. Nijesh's question is, have why doesn't name node have a replication factor of 3? The question problem is, if there were three different name node doing three different tasks, what would happen is the whole file system will become inconsistent, because name node is maintaining the all concurrency problem. If there are two people trying to write to the same file, there are two people reading the same file, and so on. All of that complexity is handled by name node. Therefore, if you try to make the name node multiple copies of name node, so what would happen is the name node will not be strongly consistent. Right now, the name node is strongly consistent. Very good question, Vaibhav, Kunal, and Nijesh. All right. Any other questions before we call it a day? So again, when a user want to write some data, let's say user, this is a client, and client is reading the data. Client goes to the name node saying, hey, I want to read this particular file. Now name node will tell client that talk to data nodes and get your data directly from the data nodes. Now if there is another client which is trying to write the data, it will first go to the name node, do the metadata operations, and then we'll go to each individual data nodes and we'll start writing the data onto the data nodes. And once it has finished the writing to the data nodes, it will inform name node that, hey, we are done. I am done writing the data. And parallelly, to create the replica of each of the blocks, the communication between data nodes will start happening. Okay. So that's pretty much about HDFS. Okay. The same thing is demonstrated here like this. All right. So we will talk about rest of discussion about how does yarn work and how does all of these components along with zookeeper and everything from tomorrow onwards. All right, we'll take a deep dive, a little bit more dive into HDFS tomorrow, and from there we will continue our discussion. All right. All right, that's pretty much for today. If you have any questions, feel free to let us know. Now, Nijesh's question is data node necessarily a separate machine or can it run as a virtual machine? So that data node as well as all of these are basically processes. Okay. These are basically processes which data node is basically a process which listens to a network commands and then does the job locally. It can run along with the name node, it can run inside virtual machine, it can run anywhere. All right, as long as the port it wants to run on is empty. Okay, so but it is strongly suggested that data nodes should not be writing the data to a file system which is itself remote. A common psyche is that okay, we will buy a cloud based file system and we will let the data node store the data files in the cloud based system, but that is humongously inefficient. When we understand yarn, then we will understand why it is not reasonable. Now, Akshita's question is how is multi-threading handled? What if client 1 reads some data and client 2 wants to edit the same data? Okay, so the writer, whosoever comes first, if somebody is writing the data, it won't be allowed to read. Similarly, if somebody is reading the data, it won't be allowed to write the data. Some other client will not be allowed to write the data. All right. Thank you, Kunal. I am happy that you liked the session. All right. All right. Have a good day. And yeah, that's pretty much. So we'll not be discussing anything else. So session tomorrow is at 7 a.m. to 10 a.m. Okay. All right. Nijesh's question is for multi-user access to a file, is it OS locked? So basically, name node is the main gateway. Therefore, name node will tell you that it is locked, so don't write to it. Okay. And but if you want to tamper the file system, you're free to do it on the local file system. All right. Recording will be made available by in like 4 or 5 hours to all of you. And all right. Uh, Thank you, Nijesh. Thank you, Sushil. I'm happy that you liked the session, Nijesh. Thank you, Vaibhav. Thank you, Gokul. I'm happy that you liked the session. So Satyendra's question is, what can you cover the prerequisites for Hadoop? For this particular course which we are running, we expect the individuals to know basics of databases, basics of command line if you are comfortable with command line. Third is, it will be great that if you know any programming language. Okay, you should know some programming language because most of the concept revolve around using a programming language to access these systems. So if you're not aware about a programming language, it might get a little difficult for you. Okay, you can go to the website Know Big Data and then register from there. Okay, you can go to Know Big Data and you can just register for there. All right, Nijesh. Thank you, John. Have a nice day. Thank you, Ganeshan. I'm happy that you found the session great. Thank you, Matthew. Thank you, Akshata. Satyan's question is, if I have to learn Java and Python both, which one to go with? It's a very difficult question, but in my personal opinion, I read both, so I liked it. Okay. So Nijesh's question is this a verified course? So it's a verified course from our side. Okay. Just like Hortonworks, Cloudera, MapR, and everybody is giving their certificate. We also provide our certificate, provide you provided you perform good, provided you at least finish our project. All right. Our certificate is accepted by LinkedIn and other people. Okay, so they display it on your name. All right, great. So yeah, have a good day. If you have any questions, feel free to write us at Hadoop at No Big Data. Okay, so you can write us at Hadoop at No Big Data. All right, bye bye. Have a good day. Okay, so you can also basically you can write on reach us at No Big Data to us. Okay, reach us at No Big Data. All right, I'll just send reach us at nobigdata.com and the website is www.nobigdata.com. Those who are student, they can write to us at Hadoop at No Big Data. All right. The class is on every weekend. All right. Have a great day. I'll have to rush to somewhere else. So stay connected.